Looks like we can start. Welcome back. Looks like it might be another small class, but we'll still definitely get through it. Appreciate you for making it in today. As far as the announcements goes, the big one is that exam 2 is next Monday, but that's really the major announcement for the moment. Any questions at all before we get started? Okay. As far as the exam 2 goes, doesn't hurt to reiterate some of the comments we made about exam 1. Best way to prepare for this exam is to be completely caught up with these homeworks. And I'm a little bit behind on grading them. I'm still grading sections 3.6 through 7. That's going to be my top priority on Friday morning to get completely caught up on the graded homework so that you can get the feedback on those sections. Once you're fully caught up on homework, then it'd be a good idea to take a look at the further problems down here. Definitely get started on compiling the page of notes, same as the other exams, 1 page of that size, full sides, and this can be handwritten or typed out. And you can also go up to the very top of the Canvas page, go to the blank lecture notes. If you want even further practice, you can consider these documents here. These don't have the solutions so that they're less distracting. These are essentially just giant worksheets at this point. And if you can solve those problems, then you're in great shape for the upcoming exam. So it'll be pretty similar to how exam 1 went. I'm going for an exam that's about similar length, written in a very similar style. As far as scheduling the exam, it's really the same instructions that I sent out again, just updated for the exam 2 information. Well, because of the exam, we won't have class next Monday, once again, but we'll return to class on Tuesday of that week. And I guess that's pretty much it for the comments on the exam. To keep going, to make sure we don't fall too far behind in the schedule, today we're going to keep going into section 310 and begin working on section 311. But any questions at all, folks, before, well, just the person that's here today, before we get started? Okay, well, let's jump in. We introduced the topic of linearization, and really the major concept here is we're just doing a tangent line equation. We're giving it a new label. We're calling it an L of X function. It looks like a new formula, but really when you study this closely, like we did on the first page of the notes, that really is just literally 100% the tangent line equation, emphasizing the function notation. The other concept we're going to study when we get into example 2 is the role that linearization plays. We've said since chapter 2 that the tangent line equation or the linearization L of X, those are now synonymous, is the best local linear approximation to the function when X is near the point of that linearization. So let's give this a try on the next example. This is not example 2, forgot to scroll a little bit further. Here's finally the example 2. We made a comment that this is similar to the homework problem number 6. That one's weighted as 20 points on the homework section 310, only because there's really a lot of parts that goes along with that one. And this example 2 in the notes is very parallel to that homework exercise. We want to do 4 different things. We want to find the linear approximation to the function g. Then we're going to use that approximation, the L of X function, to approximate the natural log of 1.05, the natural log of 0.99. So that's 3 parts to the problem already. And then finally, we'll graph the function and the tangent line, the linearization. To start this off, oh, forgot to set up my pens. Give me a moment here. This has to be done every single time I open the computer, and for some reason today, I just spaced it. So let me get these all set up. Gives us a bit of a mental break before we start. Okay, now we can officially start. Let's begin first by putting down the linearization formula. To find the linear approximation to that function g, we're going to use that it's of the form L of X equals g at A plus g prime at a times x minus a. Linearization occurs at the point where a is 0, so a g at a. And following the same process that we took before, really the first step is to get the derivative at x, not g prime at a, but g prime at x itself. G prime at x, this is a decent exam 2 review problem in its own right. We're differentiating a logarithmic function. The derivative of that function is going to put 1 minus x into the denominator. It's also a chain rule problem, so we must multiply by the derivative of 1 minus x. So g of x all together becomes 1 minus x in the denominator. The derivative of 1 minus x distributes into the numerator, multiplies into the numerator, it's a better way to say it, and becomes just a negative 1. So that's our first step in the process. And following the same color coding that we used before, the very next thing we calculate is the slope to the tangent line equation. That's this portion right here, g prime at a. So g prime at a is going to be g prime. The a value is 0, so we're just plugging 0 right here for the derivative. So we have negative 1 over 1 minus 0, and that gives us a slope of negative 1 altogether. So that's going to go into that portion. Next thing we did, we could have done that first, but this is the same order we did all the other problems. The next thing we did is compute g at a itself. So on the next step, g at a is referring back to the original function, natural log 1 minus x. So this is going to be g at 0, which means it's natural log 1 minus 0. That means we're just looking at natural log 1, which is nice because any logarithm at 1 goes to 0, including the natural logarithm. And that's essentially all of the moving parts. We just reassemble and say, therefore, the linearization, or you could call it the linear approximation, or you could call it the tangent line equation. It has a lot of names at this point. We're just referring it to as L of x now, is equal to, take g at a, that's 0, plus the derivative of g at a, that's negative 1, multiplied by x minus a, that would be x minus 0 in this problem. And this tells us that's a pretty nice linearization. L of x becomes just simply negative x altogether. So we're done with one portion of the problem. We have the linear approximation, or the linearization. And the punchline to all this work is, this tells us that for x near a, which is 0 in this problem, we have that natural log 1 minus x, the original function, is approximately equal to the massively reduced in complexity function, just negative x. So that's our linear approximation. Well, any questions whatsoever to this stage? Okay, now the next part of the problem says we are to use the linearization to approximate the numbers natural log 1.05, natural log 0.99. And we can certainly get really great approximations just by plugging these into the calculator. But this part's essential. When it says, and use it to approximate, to get credit on this part of the problem, we have to use this linearization, which is essentially that approximation there. And in a certain sense, that's actually kind of a tricky element to the problem. Let me highlight in this way to emphasize. In order to do this portion of the problem, we want to do this structure right here exactly to convert over to the right where the linearization is. So in other words, we're going to do this twice. If we're approximating natural log 1.05, but we're told we must use the linearization, we have to put it in terms of the original function. That's the f of x function right there, natural log 1 minus x. So we need to rewrite this as natural log. And let me reset my yellow here so we can emphasize on just this part solely. We must write this as natural log 1 minus, then put in something for x. Here's the approximation. It's approximately equal to another placeholder for x. So that part right here must be part of the problem to use the approximation that's provided in this stage. We have to put in a value for x. And once we have that value for x on the inside here, the linearization through the approximately equal symbol just says, put in the same value here and negate it. And that's our entire approximation for natural log 1.05. It's kind of a strange approximation in a certain sense. So here's how it's going to work. The only way to make this equation to come out as true, let me make sure I have enough space to put this in. Let me expand just a little bit. Okay, back to this equation. The only way this equation is going to be maintained, equality is not broken, is if we throw in a negative 0.05 here. I think that looks better with black. Negative 0.05 here. Reason for that is double negation cancels, and then you have natural log of the original thing, 1.05. But once we spot the value that goes in place of x from the original function, we carry this over directly to here, negative 0.05. And that's our approximation. It tells us that this is 0.05. In other words, the approximation to the natural log of 1.05 is 0.05. Let's check this out to see how that works, or how close we got to that approximation. So natural log 1.05 gives us, if we were to round to say 2 decimal places, we have a fully accurate answer, rounded to 2 decimal places at least. We weren't that far off. And the loss of accuracy we see here is because the input value was 0.05, negative 0.05, and we only get more and more accurate the closer and closer we are to the point at the linearization, 0 f of 0. So that's not too bad as an approximation. And it really is a strange problem because one thought is, why do this when the calculator can give us a pretty accurate answer just like this? One of the reasons that we kind of hinted at last class is this is really just a subtopic in the discipline for computer science of numerical analysis. We have to wonder exactly what did this calculator do? It has a lot of complicated routines, but the heart of the structure of how it computed that number there more accurately was it took something like this and added an additional term, maybe several additional terms, until it reached the right level of accuracy. So in other words, it's using something that goes beyond the linearization. If we're using just the 2 terms, we're pretty accurate already up to that point there. So that's one approximation down, natural log 1.05. We'll try it again with natural log 0.99. But any questions or comments first? Okay, well, let's try it out again. We have natural log 0.99. It's a tricky problem to start when you use the linearization because we have to write it in terms of the original function, g of x itself, natural log 1 minus x. So once you get the linearization here, it's a good idea to write this step down, that g of x is approximately equal to L of x, and then we just substituted in the values for the functions on the line down below. So if we can get it into this structure, we'll know what the value of x should be. So copying the same strategy, write natural log 1 minus, put a placeholder there, when we do all this, that's just our attempt to get the original function g involved. We need to involve g because it's the function g that's approximately equal to the linearization L at x. So on the next level, we can say that's approximately equal to negative of something. The values highlighted in blue are the input variables x and x on both sides of this approximate equation. And now we just have to ask ourselves, the mathematical equation, what goes in there so that when we simplify this, we get exactly natural log 0.99. Actually, it's a little bit nicer than the first one. I think the first one was challenging, a little bit more challenging because of the double negation. We can preserve this equality right here by the red dot by just plugging in 0.01. 1 minus 0.01 gives us the 0.99, so that equality is preserved. Now that we know what goes here, we can go through the linearization and get the approximation 0.01. Then this tells us the natural logarithm of 0.99 is approximately equal to negative 0.01. Now, my guess would be that this approximation is even better. The reason that ought to be true is this linearization is highly accurate as long as your value x, let's highlight this x right here just for emphasis, as long as your value x is close to the base point of the linearization. 0.05 was pretty close, but 0.01 is much closer, so we should see much better accuracy. So let's double check it on this calculator here. Natural log 0.99, excuse me, yeah, 0.99 is negative 0.01005. So we in fact have an answer that's accurate to 1, 2, 3, 4 decimal places. We're only off in the fifth decimal place in this approximation down here. So it has really astounding accuracy. We needed to compute that for a project around the house, something in engineering. I would say for a lot of projects, as long as it's not rocket science or something, that's a very, very good approximation there. Well, that's 3 parts of the problem down. The last part of this is illustrate by graphing the function g and the tangent line. The linearization is what it's referring to. And so that's going to be the last element that we'll do here on this problem, same as required for the homework exercise. So you can use Desmos if you like to get a view for what the graph looks like. Then put that graph down on paper. Here, let's plot it by hand to show what it would look like. It's a logarithmic function that we want to plot first, g of x. And the one thing you can't plug inside here is an input that would give us natural log 0 or natural log of any negative number whatsoever. So it has a problem right at 1. That becomes natural log 0. And that's what gives a vertical asymptote. Now next, the domain isn't to the right. You cannot plug in 2 to this function for g, because that'd be natural log of -1. That's undefined completely, just as 1 is undefined, but it's not a new vertical asymptote. We have to put in negative values. Next, if we plug in 0, we in fact did that once. Natural log 1 minus 0 is what we would get. We would get 0 itself. And so this curve looks about like this. It plummets rapidly the closer and closer the input variable gets to the vertical asymptote. And this is y equals g of x. Let's put a new color down for the linearization. The linearization for natural log 1 minus x, a pretty complicated function, is just negative x. The y-intercept on that one is 0. It crosses the origin, has slope -1. And this is what it looks like, roughly, plotting it by hand. So the closer and closer we are to 0, if we just use negative x instead of natural log 1 minus x, the more accurate our approximations become. So this is the illustration of essentially what we did here for those 2 approximations. And we did it. That's pretty much the longest problem on the homework for this section, 310, longest problem on these notes. For the next concepts we're going to take a look into, we're going to see what's going on with the second part, differentials, for these notes. Any last questions or thoughts before we go to the next concept? Okay, well, let's take a look into what's going on with these things, differentials. Let's put in a little bit of notes here just at the very top for some reminders, because when you see this equation here for the very first time, it is really kind of pretty weird looking. This word is also pretty dangerous as well. When you see the word differential, it can sometimes be easy to miss. So let's blow it up just to emphasize and say here, differential, as a big warning, is not a derivative. This causes all sorts of havoc in, say, an exam setting, most of all. As an exam 3 problem or a final exam problem, we really have to watch out for that word differential. If instructions say find the differential, it does not mean find the derivative. The derivative is part of the answer, but that's not exactly what we're computing for those particular instructions. Let's recall when it says the derivative is dy dx. And although we're not going to calculate the derivative this way, unless, say, we're on the final exam, just like we did on exam 1, just as a reminder, this is really a limit as h goes to 0 of f at x plus h minus f of x, all of which is divided by h. So the derivative is that thing, and then dy dx is considered one entire symbol. You can't split them apart. It's not a real fraction. You can't move dx over to one side and leave dy alone if you're talking about a derivative. So here's the weird thing. If you're in the context of talking about a differential, in the context of a differential, dy dx x are all variables. dy is considered to be one whole symbol. Dx is another one entire symbol, and x certainly is. It's easier to read. And so now we have three different parts to this problem, essentially: independent variable x, dx, and dy. This is kind of a weird concept altogether. And I think the struggle here, the book tried to do some good work in the reading to show how a differential might relate to some interesting things. But the major thing that we're going to focus on for the differential is this is needed in chapter 5. We'll use differentials for a skill when it comes to integration, the next leg of the course. And the short of it is it's a useful concept whenever you have to undo or completely reverse a chain rule, which is a weird thought already, but we'll definitely get closer and closer to those thoughts as we get closer to that section in chapter 5. So for the moment, we're just going to practice taking a differential, and then later we'll review what these look like when we're in chapter 5 to put them in good use for the skill of integration. That's going to be our major concept for this object here. So altogether, if y equals f of x, if it's a differentiable function, then the differential of y becomes dy equals the derivative of f at x times dx. So it's an interesting mash of symbols. We have to be really careful with those symbols. If it starts with y, there has to be a dy in your answer. If the variable is x, there must be a dx in the answer. So those elements must be included. We could lose some major credit on dropping either one of those. The differential is that whole equation involving both the dy, the dx, and the derivative multiplying dx. Well, that's the whole story with the differential. Any questions about it so far? Okay, let's practice taking it, which really just boils down to you're practicing taking a derivative and just putting in an entire equation and smacking a couple symbols on it. And those symbols will make a lot more sense once we get into integration. First, we have to be very careful with what the variables are in the problem. This differential in part A does not involve a dx whatsoever. Hang on, I got my colors mixed up. Let me try again. Let's keep the order the same there just for consistency and sanity. There's not going to be a dx in the problem because the independent variable is not x, it's t this time. So when we go to do the differential of y equals cosecant t, we start with dy, say it's equal to, we're going to take the derivative of cosecant t. We can do that on another line just to do this step by step. Cosecant t prime. Then we multiply whatever that result comes out as by dt. So this would be the differential. We still have to complete the derivative. So on the next line, we get that dy equals, we're taking the derivative of a cofunction, so a negative is there guaranteed. And the pattern for this one is we get cosecant t times cotangent t, and then put in the dt, and that's the entire differential. Well, it's kind of a shorter concept than even linearization was. There's nothing else to the story. We just end right at that step. So we'll try it again on a couple more just for the sake of practice. But any questions at all getting through that one? Okay, next one, same idea. We have r equals secant inverse theta. When we take the differential of this equation, r converts over to dr. It'll be equal to the derivative of secant inverse theta. We might as well take the derivative right this step. That is the derivative that goes 1. It's positive because it's not a cofunction. And it gets divided by x times the square root x squared minus 1. So that's the derivative portion. Next, the other variable, the problem, the independent variable is theta. So we multiply that by d theta. And that's the end of this problem. Now, as far as differentials go, d theta is like an ordinary variable, which means there's more than one way to write this down. You could, if you prefer, write this as dr equals, sometimes this is expressed in this context as d theta divided by x times the square root x squared minus 1, because we're thinking of this as an ordinary algebraic variable that's multiplying a fraction. It can, in fact, just multiply right into the numerator. And so that's another acceptable way to write the answer. I actually prefer the line above because I like to separate those symbols whenever I do a differential. But this is something that's commonly written, so it's good to just see it and not be kind of weirded out when you do see it that way the first time. Well, there's one more we're going to practice, but any questions so far? Okay, well, so far, the derivative part of the differential has really just been a mini review of differentiating trig functions. These are good formulas to put down for the sake of your exam 2 notes. I would recommend these. They're good ones to have memorized and down pat, but when you're still just learning these things, that's kind of a nice catch-all, a safety net, having these derivatives down for all 6 trigonometric functions and all 6 inverse trigonometric functions I would highly recommend. And this one is same kind of idea. This time the dependent variable is x and the independent variable is t. The other major thing about this one is it also involves the product rule. So when we go to write down the differential on this one, we'll go dx equals Now, when we put down the whole product rule to this thing, it's going to involve multiple terms. And then it will be multiplied by dt on the right. That's where another interesting algebraic issue comes up. dt is a variable in its own right, and it has to multiply through whatever you put down here. So if there are more than one terms, a grouping symbol is absolutely required to get the differential down right. So make sure to not forget the parentheses on this one. If the product rule comes up, that's pretty much a dead giveaway. Parentheses are required for this differential. Now, taking the derivative is not too bad. I'll differentiate the first function with respect to t. Derivative of a t is 1, so we're on our way. 1 times natural log 4 minus t. Then go plus. Next, copy t. And now differentiate natural log 4 minus t. That one involves a chain rule. The derivative for this one will go like this. Derivative of a natural log takes its input, throws it down into the denominator. You could put a 1 on top and then multiply by that derivative of the denominator. That's always going to multiply up into the numerator. So for natural logarithms, this is a common way to indicate the structure of the chain rule. So now differentiate natural log 4 minus t. 4 minus t goes into the denominator. We must multiply by the derivative of 4 minus t. We're placing that into the numerator. And so that's just going to become a -1 when we go to differentiate that last part. That's the end of the product rule at that stage. Then we have to put in dt. And now with these parentheses here, we have an algebraically correct structure for this particular differential. We just need to finalize the derivative, simplify this all down, and our work is complete. So on the next line, the final line for this one, dx is equal to natural log 4 minus t. And in the numerator, this derivative is just a -1. We could put the negative in front if we'd like. Format's a little bit better. Then it's multiplied by t into the numerator. So that's where the t goes. 4 minus t copies into the denominator. And multiplied by dt. At this stage, we're entirely done. That's the whole differential on this one. It was a little bit more work only because we had to use a bigger idea, a product rule, to finalize this derivative. And a chain rule as well, turns out. But any last questions or thoughts at all, folks? Getting through any one of these differentials here? Okay, well, we did it, folks. This is the conclusion of section 3.10, which means we're on the final section of chapter 3, which is kind of exciting. The Calculus 1 course does emphasize a lot of derivatives more than integrals. Chapter 4, the very next one, after we get to section 3.11, will be more applications on the derivative. And then finally, chapters 5 and 6 will take a look into integration. So let's take a look into the last section for the chapter differentiation rules. Section 3.11, hyperbolic functions. The title sounds kind of extreme when you say hyperbolic. I mean, that's almost an insult saying you're being hyperbolic to someone. The reason we say hyperbolic functions is because we're going to base a new category of functions on a hyperbola. That's a weird thought, but it's not as unfamiliar as it might sound, which is interesting in a weird way. When you took Pre-Calculus 2 and looked through geometry, you defined a category of functions on a circle. And the equation of the circle was x squared plus y squared equals 1. The idea, the way the trig functions were defined, is actually pretty extreme. It's a weird function when you think about it. You come up with a way to measure an angle in standard position, where counterclockwise means the angle is positive. Then you rotate an angle by the measurement t radians, where it intersects the unit circle, x squared plus y squared equals 1, gives you 2 coordinates. And the first coordinate is cosine of that angle t. The second coordinate is sine of that angle t. So we have a shaded area here. And it turns out this is a kind of a niche fact. I don't think it's emphasized a lot in trigonometry, but that shaded area is related this way. The rotation t is twice the area that's shaded here. So that's what goes down in trigonometry. It's a 2-credit course, pre-calculus 2. We had a lot to say about this. But the mind-blowing thing about ordinary trigonometry is you can make one little swap and redo top to bottom a different type of trigonometry called the hyperbolics. You can define 6 hyperbolic functions, do their inverses, do their identities, do lots of pretty routine application kind of problems. It'd be just like a different sort of reality that you're working in, some other different dimension where someone swapped a plus to a minus, and if it's a minus there, you don't have a circle anymore, you have the hyperbola. There it is, comes in 2 parts. On that hyperbola, if you let area A denote the area of the sector shaded here, then twice that area will be a value t. And we define hyperbolic cosine of t, hyperbolic sine of t, to be the x and the y coordinate on that right branch of the hyperbola. Pretty strange and complicated definition, but it's all just based off x squared minus y squared equals 1. We'll know we're dealing with hyperbolic functions if we put in an h there instead of ordinary COS for cosine. Sometimes this is read as cosh h for short, or hyperbolic cosine of h. Similarly, you could say sinh h for short, or hyperbolic sine h. Just depends on how much breath you have when you say this enough times, I suppose. So that's how the hyperbolics are defined. It's really pretty weird when you look at the hyperbola and define them this way. But it turns out there is a really nice way to define both hyperbolic cosine and hyperbolic sine, which cannot be done for cosine and sine. Turns out cosine and sine are the absolute weird ones here. Hyperbolic cosine and hyperbolic sine have an alternative and very nice definition. Before we look at that definition, any questions with the introduction to the functions? Okay, now one thing to think about is, why can't we do the same for cosine and sine when you see how we're about to define hyperbolic cosine, hyperbolic sine? Turns out it's impossible, but if you're really curious, take your calculus textbook, turn to chapter 11, go all the way to the section, I think it's 11.11 on Taylor series, Maclaurin series, and you'll find a table there that shows you how to write down a formula for cosine, how to write down a formula for sine, but it will involve infinitely many terms, which just seems like some weird and cruel joke. It's a hard function to work with. But cosh and sinh, the hyperbolics, are a lot nicer. Here's how they're defined. You get just a straight out formula for hyperbolic sine, a complete formula for hyperbolic cosine, and tangent, cosecant, secant, cotangent are defined 100% analogously as ordinary tangent, cosecant, secant, and cotangent. Ordinary tangent is sine divided by cosine. Hyperbolic tangent is just hyperbolic sine divided by hyperbolic cosine. Then the column to the right is just the reciprocal functions, and that's 100% same for the original trig functions. Where the column on the right, you would say cosecant x is 1 over sine x. You would say secant x is 1 over cosine x, and so on. So there is a lot of parallelisms here, which is amazing. But the mathematical miracle is hyperbolic sine of x is just based off of base e exponential. So that weird base e, Euler's number, just keeps on coming up over and over again. It's approximately 2.71. It is a nice derivative. The derivative of e to the power x is e to the power of x. The derivative of natural log x is 1 over x. It's also used over here to define the hyperbolics. Hyperbolic sine, you just take e to the x minus e to the power negative x, divide by 2. And almost the same song and dance for a hyperbolic cosine. The only difference between the two of them is that sign there. So good way to memorize hyperbolic sine is get that formula down, e to the x minus e to the power negative x divided by 2. If you have that down pat, just look at the trick to get hyperbolic cosine. You flip to a positive in the numerator between the two terms. And then beyond that, just use your training from ordinary trigonometry, pre-calculus 2. If, say, hyperbolic secant comes up, it's just a reciprocal of this one, which means secant h at x is really just 2 over e to the x plus e to the power negative x. It's just the full-on reciprocal of hyperbolic cosine. So those are 6 brand new functions that we've defined first by these two, and then everything else is a recombination of the sine and cosine version. Before we get into the calculus of it, we should do a little bit of algebra. We'll do some function evaluations, look at some graphs, and then we'll take a look into some identities and finally the derivatives. But I think it's kind of rude to just define 6 new functions and not practice with them first. So that's what the next examples are all about. Before we practice with the hyperbolics, any questions at all so far with their nicer definitions? Okay, well, let's do some evaluations. And it's good to take a step back and think about how tricky this is in a real sense. For example, if someone asks you to evaluate sine 5 pi over 6, you might have that down pat just by memory, but if you were to say, if you're a little rusty, you might do something like this. Put down a unit circle, think about the radian measurement, 5 pi over 6. It's just short of pi, which is 6 pi over 6. So 5 pi over 6 is 36 degrees short of pi. You're right here. Sine is the y-coordinate, which on this pretty crude diagram is 1/2. Turns out that's accurate. Sine is positive 1/2 at 5 pi over 6. That's a weird way to do a function evaluation when you think about it. We go back to the geometry of the unit circle, find the rotation, see where the terminal point is, and get a coordinate out. It's kind of laborious. There's lots going on. If you're dealing with hyperbolics and it just says sine h at 3, all you're doing is plugging in 3 into that input variable for x. So this just becomes e power 3 minus e power negative 3 divide by 2. Similarly with the homework, we're going for an exact answer in simplified form, and that's exact. It doesn't really simplify in any reasonable way. I would just leave it in that format. And so we're completely done on that one. So it's again good to step back and think about what's going on with sine and cosine and all the other trig functions. They are absolutely much more technical functions in a real sense. The hyperbolics are quite a bit easier to work with, way easier to define. Why didn't we do hyperbolics instead of original trigonometry? The problem is trigonometry is just useful. It describes periodic motion, which occurs everywhere in nature. And so because of their massive applicability, that's why we study the original trig functions before the hyperbolic ones. But there are good applications to these functions. There's plenty in the reading. We'll look at one in the notes if we have some time. And so it's just another useful class of functions. But we'll try out a couple more just for the sake of practice. Next one is asking us to calculate hyperbolic secant of natural log 10. One thought here is, if it's a secant version, it's just 1 over a cosine, but it's the hyperbolic version. So this is 1 over cosine h at natural log 10. That's not a bad thought, but maybe a more useful thought is, if you take the reciprocal of cosine h at x, all you're really doing is plugging 2 in the numerator We'd eventually get there algebraically, but this would become a complex fraction and it would require another step. So it's easier to visualize it this way. Flip it around, put 2 in the numerator, put e to the power natural log 10 plus e to the power negative natural log 10 into the denominator, and that's hyperbolic secant at natural log 10. Now, we do have to simplify this down. We want the exact answer as well for these problems. There's some really great simplifications here. We've practiced quite a bit of logarithms, reviewed them quite a lot. There's a nice cancellation that goes on here, so the first term is just 10. But word of warning, this only came up once, I think, in the prior sections. I think section 3.8 probably. There's no cancellation there until we move that negative sign out of that position. So e and negative log is not inverse to each other. So we do need some more properties of logarithms to simplify this down. But that's just as well. This is good algebra review. We'll copy 10 from the first cancellation. And now over here, let's go plus e to the power of something. The property of logarithms that we require is a coefficient here, which is a -1, becomes an exponent. This is e to the natural log of 10 to the power -1. So move that negative around like so. And now, and only now, can we do the cancellation. Those functions are inverses to themselves. And so we just get 10 power -1 after the cancellation. So this is on the next line, 2 over 10 plus 10 power -1. This one actually simplifies a little bit more, so let's keep on going. Best way to simplify this is to clear the denominator. 10 power -1 is really 1 over 10. So if we multiply the whole thing by 10 over 10, we can simplify this down. Numerator becomes 20. Distributive law in the denominator will give us 100 plus 10 times 10 power -1 is just 1. So this is altogether 20 over 101. And there's really nothing more to say to that. This one took a little bit more steps because one thing that's interesting about the hyperbolics is if you plug in natural log of a number, because these are based off of base exponential, there's cancellations, and you get a nice fractional number like this very often. If you plug in just say 3, it's probably going to be an irrational number like this one we see here. Well, that's 2 down. We'll practice with one more here, hyperbolic cotangent. Any questions or comments so far? Okay, as far as hyperbolic cotangent goes, always go back to your original training with trigonometry, pre-calculus 2. A cotangent is always a cosine divided by a sine. The co tells you what's in the numerator, a co-function in the numerator. So if it's a hyperbolic cotangent, same idea with the hyperbolics. It's kind of nice that the logic is essentially identical. We're just throwing in the h for the new class of functions. So hyperbolic cotangent 2, you could break this down step by step as hyperbolic cosine at 2 divided by hyperbolic sine of 2. So make sure the h's are in there. That's going to make a difference in our answers, critically when we're doing a derivative. Beyond that, we need to know how hyperbolic sine, how hyperbolic cosine are defined. Notice that we're forming a fraction of 1 divided by the other where there's divisions by 2. So you can take a shortcut here, but for the sake of the notes, let's write this out in full. Hyperbolic cosine, I'm going to write this equation here, kind of going sideways, as e to the power 2 plus e to the power -2 divided by 2. Then hyperbolic sine at the input 2 is e to the power 2 minus e to the power -2 divided by 2. Almost the same thing with that one difference. The middle term numerator has an opposite sign. But once we've done all that, if you're dividing by 2 like this, that is a cancellation if you're dividing by the same quantity, both numerator and denominator. So that's the shortcut there. You never really had to put division by 2. if you're doing a hyperbolic tangent or hyperbolic cotangent. The divisions by 2 just cancel out. And so this becomes altogether e squared plus e power negative 2 divided by e squared minus e power negative 2. And beyond that, there's really no cancellations here. You can rearrange it a little bit more algebraically, but I'd say just about any form is about as simplified as the other at this stage. Just like on part number A, this is a good stopping point for part C as well. So that's the whole story for cotangent hyperbolic at 2. It's kind of messy, but it's nice and satisfying, more satisfying in a way, because we have some really great definitions for every hyperbolic function. We never have to do this kind of stuff, argue geometrically and pull coordinates. Well, that's the rundown on how to evaluate the hyperbolics. Next thing we'll take a look at just briefly, because whenever you are in an algebra setting and you define functions, we should look into their graphs. So we'll do that briefly. Let's take a look into all 6 graphs of these functions. So as far as the graphs go, this page down below is really just here for completion. It's not something that you have to endeavor to memorize. If you have a really, really good visual memory and you just do memorize it, no harm done. I took this for a particular textbook that just had some really nice graphs for these functions. First one is hyperbolic sine. It's this curve in the middle, and the dashed line are just asymptotic curves that it approaches. So it has domain, range, all real numbers. Hyperbolic cosine, if you make a flip to plus instead of minus, here's the curve. It's not exactly a parabola, but it seems to remind us of that shape. Domain is all real numbers, but the range is bounded at the lower end at 1, off to infinity. Then tangent, cosecant h have their own particular curves. Secant h, they seem to change quite a bit going from one to the other. And hyperbolic tangent, again, big change going from one to the other. Just for the sake of completeness, here are all their graphs, all their domains and range. So this would be a good one-stop shop if maybe you're doing something else in an engineering class, and if you have to look up one of these domains and ranges to see if you can solve an equation, this is a good page to come back to. Again, for our purposes in this class, really just here for completion. We just should know what these functions look like. Much like if you're in a trigonometry class, it'd be rude to never show that y equals sine x is that curve. If we never see this in a trigonometry class, we probably got shorted on our education in that class. But aside from the quick look at these graphs, any questions about them? Okay, now let's bounce around just a little bit and go back up to the top page. So when we define trig functions geometrically this way, it's through the unit circle. When we define the hyperbolic functions this way, through the hyperbola, we use x squared minus y squared equals 1. But when you start off with those ideas, it implies just immediately some really nice identities. If cosine t is the x-coordinate and sine t is the y-coordinate, we're really literally saying cosine is x, sine is y. So when you look at this equation, x squared plus y squared equals 1, it just means cosine squared, I guess that's t, plus sine squared t is 1. So we get that sometimes called a Pythagorean identity just immediately. And same idea over here, if you're defining things through the hyperbola, where you pull coordinates for hyperbolic cosine, hyperbolic sine, x is hyperbolic cosine t, y is hyperbolic sine t, also solves that equation, so we get the next identity. Hyperbolic cosine, cosh t, squared, minus sinh t squared is 1. So it's almost the same identity. It just has the difference of plus going to minus. By the way, these curves were defined on these geometric objects in the very first place. That was the only difference in the equations. And so the identities are also very similar. And there are a lot of trig identities. Depending on how you're counting them, you might be on the order of magnitude of 40 identities, maybe pushing 60 identities. Same idea with the hyperbolics. For essentially every trig identity you put down, there's a dual identity for the hyperbolic functions. And we're just seeing it for this one basic identity here to here as well. So these identities are copied down below. Well, this one in particular. Let's take a look at the full list of, well, not the full list of all hyperbolic identities, but these are the ones that the author decided to put into the reading. So I copied them down verbatim as well. We're not going to use a whole lot of hyperbolic identities, but it's good to know they're out there. If you're working with a lot of hyperbolic functions, this would be one place to look, and there's an even bigger category of them out there. First set of identities are the odd even function identities. These are nice because they go exactly the same way for sine and cosine. Sine at negative x is negative sine x. Cosine of negative x is cosine x. So it's a verbatim, completely the same identity. This is the one that we were looking at the very top of the notes. Hyperbolic cosine minus hyperbolic sine equals 1. That's where there is a difference. Cosine squared x plus sine squared x is a positive 1. There's one for hyperbolic tangent relating hyperbolic secant. There's also addition formulas. So we have several addition formulas here, and there's more if you put minuses inside of those. But really what we'll do is we're not going to spend too much time working with identities because we want to get into the calculus before we run out of time. The major homework is going to be about the calculus as well. So we'll just spend a little bit of time here just showing how does a proof of one of them look like. Proofs can sometimes be pretty hard in trigonometry. Proving something like this was never too bad, but if you had to prove something like, say, this in a trigonometry class, the proof of the addition formula, there's lots of different kinds of proofs, but that involved a lot of ingenuity, a lot of geometry, rotating things around, using distance formulas. But they're not too bad for hyperbolics because we have great definitions to work with. Let's prove this one. This is the even identity for hyperbolic cosine. The idea here is we just cite the definition for hyperbolic cosine and work directly through it. Cosh, I'll say at a, is going to be equal to e to the power of a, involves a plus for this one, e to the power of negative a, divide by 2. So if we're going to prove this identity, we start on one side, hyperbolic cosine of negative x, do some algebra, try to link up with equality, several steps, hopefully not too many, until we land on ordinary hyperbolic cosine. But all we're really doing for this identity, again, it's probably a little bit nicer than trigonometry, is just take negative x, plug it in for a. This becomes e to the power negative x plus e to the power of negative x all over 2. And then when we simplify these down, we can also swap their order. We can put this term first. That's just e to the power of x. Then go plus, we can make that term be second, e to the power of negative x. Divide by 2. But the moment we simplify the negation, swap the order, we didn't even have to swap the order. We just did that for identification purposes. We can identify this as being just hyperbolic cosine of x. The work is just completely done right at that stage. It's kind of amazing in a certain sense. These don't take too long. They're not really drawn out. Didn't require a lot of ingenuity. We just use the base definition for the function in the first place. Well, that's our quick tour of introducing the 6 hyperbolic functions and doing just a bit of algebra with them, evaluations, proving an identity. But because it's a calculus course, the major thing we're interested in are their derivatives. So that's what we're going to take a look into very next. Any questions so far with any of these functions before we check out the derivatives? Okay, well, before we take a look into the derivatives, here's some review. These are the original trigonometric functions. This is always going to be important. This is an incredibly important table to any calculus class, any class that uses calculus as a prerequisite. We have derivative of sine is cosine, derivative of cosine is negative sine. Interesting patterns we mentioned before are every time you differentiate a co-function, a negative sign will pop out, and there's relationships. If the derivative of sine is cosine, we'll change from sine to its cofunction, and cosine to its cofunction. The cofunction to cosine is just sine itself. Swap those around and you have a new identity. Likewise, if the derivative of tangent is secant, change tangent to cosecant, or excuse me, tangent to cotangent rather, like we have here, change secant to cosecant, and you have the next derivative. You just have to remember to include the negative sign. So there's a relationship between the function and its cofunction as well. So that's the pattern of attack for the original trigonometric functions. Now when we look into the new category of functions that we define in these notes, the hyperbolic ones, here's how these go. Here are the derivatives of all of the hyperbolic functions. It's remarkably similar. There's one place to really be very, very cautious with. If you liked how we organized the signs on the table above, there is one break on that pattern. The negative sign that you would expect to be right here is not there. The derivative of hyperbolic cosine is hyperbolic sine itself. That negative you expect to be here actually goes over here. So the rule of differentiating a cofunction to get a negative sign, that only works for trigonometric functions, sadly. That's sort of unfortunate, but that's how the work goes for these kinds of things. We just can't get around the fact of that. Aside from that one key difference highlighted right here on that sign, everything else is identical. That's kind of impressive. So watch out for the fact that derivative of hyperbolic cosine is positive hyperbolic sine, and that we have a negative here for the derivative of hyperbolic secant. But if you're looking at, say, all the rest of the rows, say here to here, the last row here, here, as well as this and this, oh, hang on, not that one. Those are the ones that are off. As far as the top row goes and the bottom row go, all you're going from one derivative to the other category of functions. The only change is we put an h in it to make it a hyperbolic function. And that's really, really nice. It helps our brain organize how these derivatives go. We don't have to have too much kind of overthinking going on, not always constantly looking up a formula every time we have to use it. So paying attention to those patterns is really critically helpful for these kinds of derivatives. And that's what we'll do next. Just practice taking some derivatives. Before we work through some practice problems, dealing with this last category of new derivatives for chapter 3, any questions or comments at the moment? Okay, well, let's work through these, see how they go. First derivative, is actually kind of tricky in a way. We know that the derivative of hyperbolic cosecant is negative hyperbolic cosecant times cotangent. But that's not the whole story to this function. There's a power 2 here, so it's also a chain rule problem. And it's tricky to do a chain rule sometimes when you're dealing with trigonometric or hyperbolic because of the way we write in the power. So let's reformat the function just to emphasize that f of x is really, in a different format, cosecant h at x, power 2. Writing it this way reminds us that the inner function is hyperbolic cosecant x, The outer function is the power 2 function, and that helps us quite a lot when we do this one with the chain rule. So let's hit it with the chain rule, see what we get out on this. The derivative of f at x is first, we differentiate the outer function, the thing on the outside, the power 2 function. That goes like this, 2 to the power 2 times something to the power 1 is a better way to say that. So we use the power rule there. Then we chain on a new derivative. So that's just a power 1 to emphasize the power rule. That's the actual derivative symbol there. And then we plug in inner function, cosecant hx here, cosecant hx goes here. So we'll simplify this by dropping the power 1 and the parentheses, and then just take one more derivative. So that's our start with the chain rule. On the next step, we have that this is equal to 2 cosecant h out of x. Then the derivative of this one becomes negative cosecant h at x times cotangent h at x. And it simplifies in a decent way. We can consolidate the negative up in front, but we have like bases. We should always combine those together. So this becomes negative 2 cosecant h squared of x. So those are the like bases combined times cotangent h of x. So that's the whole story on that one. And really, we only use the table once right here for that derivative, for the hyperbolic cosecant h. And if you revert back to how we did it in section 3.3, the only difference, once again, this is an important point to emphasize, is we just put an h in for both functions to get the right derivative. So that's one down. And this is how we'll end our work today. Let's just practice a few more of these as we go. We'll practice chain rule, product rule, quotient rule, those kinds of good things. Any comments on getting through part A? Okay, well, let's try it out again. This time it looks like we're dealing with quotient rule in this setup. And watch out for the small things. It's all in the little details. The numerator is hyperbolic, but the denominator is an ordinary trig function. You have to be very cautious with that. Also, maybe just to emphasize as well, let's write in this comment. The h, let's try and put quotes around, that just looks weird. I'll just write it this way. The h must be here in the answer. So when we take the derivatives of a hyperbolic, we have to have those h's in the answer. So the presence or the omission of a h is really, really critical for these derivatives. You have to say what we mean exactly what we say, and exclusion or exclusion of the h does make a massive amount of difference. Aside from that, this is just a good old quotient rule. We usually organize in this way: the function on top, the function on bottom. Then as far as the quotient rule goes, here's the pattern of attack. dy dx becomes, it's a fraction, so let's put in a big bar. Hopefully that one's long enough. We differentiate the numerator on our very first term. It's a hyperbolic sign that just changes over to a hyperbolic cosine. So 5 cosine h at x. We multiply it by the denominator copied, cosine x. In a quotient rule, we go minus. Next, copy the numerator, 5 sine hx. And then we multiply it by the derivative of the denominator. The derivative of the denominator is a negative sign. So let's put it in parentheses to make sure we're saying multiply, not subtract. Negative sine x. You could take a shortcut here and just drop the parentheses in the negative sign and just write that in as a positive. That's going to happen eventually. I usually don't do it in my notes because it makes the step look kind of crazy if you came back to it. If you did it in your own work, that'd be an appropriate shorthand to take. The denominator finally is just going to be cosine squared of x. So the parts in the color coded are where we took the derivatives. And aside from that, we just need to simplify this down. There's not a whole lot to do. The end result is 5 cosh x times cosine x plus 5 sinh x times sine x divided by cosine squared x. I don't see any reasonable simplification whatsoever on this kind of thing. So we just end right at that step. Well, that's the run through the quotient rule, dealing with the hyperbolic derivatives. Well, we only did one hyperbolic derivative on this one. But any questions or comments getting through it? Okay, well, we've got more to take a look into, so let's try out the very next one. Here's the table once again for easy reference, since we just barely took a look at it. Let's keep it here for us as we go. So this one looks like it has a good amount of stuff going on. There's two terms, but the first term we have to be really cautious with because the first term here is going to involve the product rule. Aside from that, not as bad as probably even the last problem. So let's work through this derivative. In the product rule, we are organized by first factor and second factor, and just differentiate in a very similar way, except no denominator, a plus in the middle. So let's work out the product rule portion first. F prime at x is going to be, take the derivative of x, that's one of the nicest derivatives ever, we just get 1 times, copy down hyperbolic tangent h at x. Then we're still doing the product rule. We go over to the first factor, x again, go plus and copy it down. Then move over to the second factor. We're going to multiply by the derivative of tangent hx. If that was just tangent, its derivative would be secant squared x. And if it's hyperbolic tangent, it's just hyperbolic secant squared at x. Again, that's an amazing and wonderful pattern to have. The fact that ordinary trigonometry and hyperbolics are this close with their derivatives is pretty amazing and impressive. So secant h squared at x is the derivative for the hyperbolic tangent. And at that stage, we're done. We're on our way. We just move on to the next term. We'll go minus. Here we need to be really cautious. You'll recall that if you differentiate cosine, you get negative sign. But here's where the pattern breaks down. Row 2 took a negative you expect here and moved it over to the other column. That's kind of weird and random. If you differentiate hyperbolic cosine using first principles, this is just the result you get. There's no way to undo this result. So when you copy the negative sign, differentiate hyperbolic cosine, you just get hyperbolic sine h at x and no sign flippage whatsoever. If that said minus cosine x, the result would have been plus sine x. So that's always something to watch out really carefully for. The presence or omission of a h there makes all of the difference in the derivative sometimes. Well, that's the end of the story of this one. Some of these go a little bit faster. I think some of them are trickier or take a little bit longer. Any questions at all, folks, finalizing this one? Okay, here's the next one on the list. So this time we have g at x equals hyperbolic secant squared of e to the power 4. This one's tricky. It's tricky because there's a temptation sometimes, especially when we have a brand new set of formulas, to go to this shiny new formula here. We know that the derivative of hyperbolic secant at x is this entire structure here. But if we use that for this right here, we could lose all of the credit on this kind of problem. We have to be very, very cautious sometimes, especially on, say, exam number 2, exam number 3, the final exam, and always have a sharp eye for constants. For example, if y equals 5, then y prime is 0. But that's the easy one to spot, right? It gets trickier if you say y equals maybe sine 5. This looks like it's somehow bigger than a constant, but it's not. Just because you put a sign there doesn't change the fact that you're just looking at a number. This is the irrational number that goes negative 0.95 and some change. No different than 5 by nature of being a constant. So the derivative of sine 5, it's still just 0. And same story on this one. Just because we have a whole bunch of fancy things going on here, different functions, the hyperbolic secant, power 2, base c exponential, doesn't change the fact that this is also constant. It's constant because no x appears there whatsoever. If we want to emphasize that it's constant, we could compute it. Secant h. I'm not sure how to do hyperbolic secant. I'm gonna have to look that up. That's something I don't particularly know how to do in Desmos. Well, either way, hyperbolic secant h squared of e power 4, much like something like sine of 5, this is constant. And the whole answer to this one is just g prime at x, nothing but 0. And I'll look up that on my own time, figure out how to put in a hyperbolic function for Desmos. I guess this is the first time it's just ever occurred for me to try. Any questions at all, folks, on the tricky one in part D? Okay, once again, watch out for disguised constants like that in exam 2. It's a critical skill to always be able to identify them and differentiate them as a value exactly 0, as we did on this one here. Now let's try out one more, and then we'll change gears to the application with the last time that we have. I think that'd be a good call for what we've got left. Here's the full table, and this time we're taking the derivative of hyperbolic sine times hyperbolic secant at these weird values, ax plus b, ax plus beta. I think that's a typo there. I think that was meant to be alpha to go along with the beta. So sorry for that quick edit right there. So alpha x plus beta along with the ax plus b. This one is not the worst problem in the world. It's just a long one. It's going to be a product rule. So this is going to be our first factor. This one will be our second factor in that product rule. And that red kind of just disappeared. So let me just put here a quick note. Alpha, not A, I think is what the original intention was for this problem. So go to differentiate this, and here's what it would look like. F prime at x is going to be, following our ordinary pattern of attack for a product rule, we'll differentiate that first factor. Derivative of sine h becomes cosh ax plus b, but it's also a chain rule. We have to multiply by the derivative of ax plus b as well. Once we have that down, we copy hyperbolic secant h, and that's an alpha, x plus beta, go plus, Copy this function down, sin h, ax plus b. And now here's our next derivative, hyperbolic secant. And this is the really dangerous one. Hyperbolic secant does in fact involve a negative sign. So let's go here with a negative sign. It goes secant h of something. You know what? I'm a little worried here. I'm going to run out of space horizontally. Let me backtrack for just a moment to make sure I can fit everything on a horizontal line. If you're running out of space horizontally, the strategy to take is just go down a line and continue on. So I'm writing down sin h, ax plus b. Now doing this derivative. I think this is the first time we just ran out of horizontal space. Derivative of this one goes negative secant h of something times tangent h of that same thing. Then it becomes a chain rule, just like on the first one. We take the derivative of whatever that thing was, and it's alpha x plus beta in all three positions. It's a tricky derivative to do a derivative for secant h because it has two spots where we put in the input. If it's something more than just x, there's the third spot right here for the chain rule. So alpha x plus beta here, here, and here. There it all is in one line. Well, staggered, dropped down a little bit to make it happen. We have to take that derivative there, this derivative way over here, and just rewrite everything. Our work will be done on this one. So that's the setup to start. Any questions at all, folks? Just writing down everything with the product rule and the chain rule portions. Okay, here's the conclusion to this one. F prime at x is going to be, I'm going to take this derivative here and just move it out to the front as a coefficient. That's a degree one equation. So the derivative is just the coefficient a for x. So we'll get a times cosh ax plus b secant h alpha x plus beta. And then tempting to say plus, but it looks like it's going to be a negative sign. Due to that negative sign, we can move it out in front and go minus. We're going to copy all this stuff in, the negative sign already there, but we need to do this derivative. But it's the same kind of idea. The beta is a constant, it goes to 0. We differentiate x to the power 1, x vanishes, and we just retain the coefficient, alpha. So this becomes minus alpha. And then copy everything else down, sin h, ax plus b. We already put in the negative, so we skip over to secant h. Let me fix that b first, that looks kind of funny. Secant h, alpha x, plus beta, times tangent h, alpha x plus beta. And it's a pretty messy derivative, but here's the whole conclusion. Lots of terms on this. I'm not sure if this can simplify in any reasonable way. I guess you could factor out to secant h, but it would be to very little benefit. This is a good stopping point, I would say, for this one. But we did it, folks. That's the full tour through these derivatives when it involves hyperbolics. Really, it was a good opportunity for us to just kind of review how the original derivatives go for trigonometric functions, because there's just an adjustment in row 2, moving that negative sign over. It was also a good opportunity for us to review chain rule, quotient rule, product rule, and product rule with the chain rule all at once in part E. What we'll do next is take a look into an application. I'll try not to take up too much more of your time as we're running out pretty rapidly, but this is what we'll end on with our work today. The notes and the reading goes a little bit further still. And I put this here on the last page really for the sake of completeness. I didn't ask any of these questions in the homework assignments, which means I am forbidden for asking these kind of derivatives in an exam setting. But if you're curious, you can invert the hyperbolics when you restrict their domains, just with original trig functions. And then you have derivatives of the inverse hyperbolic functions. And again, this is mainly for the sake of completeness. If you're curious on how they go, this is a good place to look them up. Also in the reading, but these will not come up in the homework or on exam 3 or the final exam. These are kind of more now rare derivatives at this point, less common to come up. The last thing we're going to resolve is just what applications you would use hyperbolics on. There's lots of interesting applications of they would model the height of a cable going from, say, one telephone pole to another telephone pole. The way the cable sags is modeled by hyperbolic functions, which is kind of interesting in a way. But it's more diverse than just that famous one, the cables. Here's one nice application that tells us if a water with wavelength L moves with a velocity v in a body of water at depth lowercase d, then the velocity of that wave is modeled in this way. G is acceleration due to gravity, and L is the length of the wave. D is the depth of the water. So here is the speed of the wave as it propagates through. That's an important application in the sense that waves like these can occur. Say if there's a massive earthquake in the Atlantic Ocean, Pacific Ocean, people want to know what might happen with a tsunami wave as it propagates to the ocean. Turns out those move extremely fast. I was kind of shocked to learn they move about as fast as a jet airliner. And this is how they can model these things. They slow down when they reach shore, but that's when they get really, really tall, tragically. So we want to explain for this shorter application why the approximation velocity equals just the square root of GL divided by 2 pi is appropriate for deep water. So it turns out this model is a little bit better for more shallow water, apparently, but in deep water, this is a better model. So here's how we're going to attack this kind of problem. When it says deep water, we're talking about something getting large. That would be lowercase d, the depth of the water itself. So we can interpret this problem as, for making this approximation, we're taking the limit as the depth goes off to infinity. We saw this kind of limit come up once before, I believe in section 3.7 in population dynamics, modeling the population of, I think it was yeast cells. We're taking the limit as d goes to infinity of the velocity v, which would be the limit as d goes to infinity of a square root function. But as far as limits go, the limit can go inside that square root function, multiplying GL over 2 pi times tangent h, 2 pi times the depth over the length. So by the constant multiple rule for limits, the constant here stays exactly as it is. And what we're really doing is we're taking the limit of the hyperbolic tangent function. Some of the limits that we've looked at when it goes to infinity, they involve graphs. For example, when we took the limit for a tangent inverse as the input variable goes to infinity, we said it was 2 pi because that's a horizontal asymptote on the graph of tangent inverse itself. This was all the way back in section 2.6. So it's good review on limits in its own right. And here's one good use for the graph of the tangent function. Here it is. Let's screenshot it into our problem. The hyperbolic tangent function, better said. It's always good to be specific. Which tangent do you mean precisely? So based upon this information we have about the graph of hyperbolic tangent, we know that as the input variable gets larger and larger, goes off to infinity, it approaches a horizontal asymptote of exactly 1. So limit as x goes to infinity of tangent h of x is 1. And even if you're multiplying by 2 pi divided by L, it's going inside here, it's getting larger and larger. It's getting closer and closer to a height of 1. So the resolution to this limit is, it just becomes square root GL divided by 2 pi times 1. So the hyperbolic tangent portion, turns out it's important if you want to know the exact velocity of the wave. If you know you're talking about very, very deep water, you can approximate pretty well through this limit right here, GL over 2 pi. That makes this a reasonable approximation for very large values of the depth of the water D. Well, that was our application. Really, it was just a way to think about the good uses of a hyperbolic function, like the tangent one. Loop in the graph, since we didn't really use it much, but here we used it in a great way to take a limit. It was also just a review on doing limits at infinity. This was something we did all the way back in section 2.6. It turns out we're going to do it again. We hinted at this. We're going to look at limits again using a rule called L'Hopital's rule, where we take into account derivatives to help us do these kind of limits. But this is just a kind of a refresher on how to work with these kind of limits for the moment. Well, I think I ran out of things to say about this section. This is the full tour of what we're doing in the hyperbolic section. This content, like we mentioned before, is going to be information that comes up on exam 3. But as far as exam studying goes, exam 2 is going to end at section 3.7. And I'll be working, like I mentioned at the start of class, first thing on Friday morning, getting caught up with the grading. If you have any questions whatsoever about the exam, don't hesitate to reach out. I'll be checking my email every day, usually typically around the morning time. But any last questions or thoughts whatsoever, folks, before we call it a night today? Okay, well, this looks like a good stopping point for us. The next place we would go is chapter 4, but I don't think it's a good idea to crack that one open just yet with the limited amount of time we have. After we get through exam 1, which is on Monday, we won't hold class on that day, so in case people schedule it during the class time. On Tuesday, we're going to move over into chapter 4 and start working through this information here. But have a great night, folks. I'll see you all on Tuesday's class, and don't hesitate to reach out once again if you have any questions while you're studying. Take care. Yeah, I'd be happy to. So 3.711b, let me take a look at that with you. Oh, I think I recall how this one goes. Let's put on the notes here as well. I'll save this and upload it in case you want to come back to this place here to take another look at it. So it says a rock thrown vertically upward from the surface of Mars, the velocity of 15 meters per second. If that happens, its height is this. To do part B, we really need to do part A, but that's kind of a fast part, right? We just take a derivative. You could call it dH dt. It's also a velocity, so you could also call it just v at t. Let's do both, why not? Just to emphasize, v at t is the derivative of h with respect to t, which is 15, and 1.86 times 2 is 3.72 minus 3.72 t. So we get that velocity there. We want to know the velocity of the rock when it's 25 meters on the way up and 25 meters on the way down for its height. Well, that just says that we have to go back to the position function, the height at any time, throw in 25. 25 is now equal to 15t minus 1.86 t squared. The reason we have to do this is to get the velocity at the rock at a specific height, 25 meters on its way up, on its way down. We need to know the time at which that occurs. So we throw in the height, solve for the time, and we're expecting two valid values, which we're going to use. Does that make sense to that stage of the problem? Awesome. And if this was a problem that, say, was going to come up on an exam setting, it would factor really nicely. This one doesn't. This one does not factor nicely at all. So here's the steps we would have to take. We would begin by putting 0 on one side, negative. You know what? Let's maybe move it around this way. I want to get 0 on the right-hand side. I think it's just slightly more convenient. Add 1.86 t squared to the opposite end. It's just more comfortable to make that coefficient positive. Subtract 15t, go plus 25. Now, this one is not going to factor in a reasonable way. So we just hit it with the quadratic formula instead. So it's a kind of a nice review from that concept from a while ago. We need the discriminant, b squared minus 4ac. The b coefficient is negative 15, so we'll go negative 15 squared minus 4 times a, 1.86, times c, 25. And now it's time for the calculator on this one. The discriminant becomes negative 15 squared. It's just guaranteed to be positive, but we threw the negative sign in there just so we know we don't forget it. Minus 4 times 1.86 times 25. So we get a 39. If that was a 36, which is a perfect square, that would be a giveaway that this factors, so we don't need the quadratic formula. But that's a prime number, so we really need it this time. So now t equals negative b plus or minus the square root of the discriminant, 39, divided by twice a. So t is now negative b, which is now negative of negative 15. Let's call that just a positive 15. Add or subtract root 39 over twice a. I think we did that once when we differentiate here. That'd be a 3.72. Now for this problem, I think it makes reasonable sense to get approximation for the time values. So let's get our two roots to the quadratic. They go 15 minus square root 39, divide by 3.72. So our first root is 2. I think 3 significant digits make sense, 2.35. And this is in seconds. I should really say t equals, that makes better sense. T equals 2.35 seconds. And then do it again. Here's the second root, 5.71 seconds. So with those two values there, we take both of them. If we want to know the velocity of the rock on its way up, that should be after it was initially thrown. So that looks like it's on the way up 2 seconds later. It's going to eventually reach a maximum height, start coming back down. And that looks like that's when it's at 25 meters on its way down. We want the velocity at both of those times, which means that's the velocity at any one time whatsoever. Plug 2.35 here for t, plug 5.71 here for t, and you'll get your two velocities. And there's a big check on the problem because it's on the way up. This means v at t has to be positive, bigger than 0, because derivatives convey speed and direction at the same time. And this one, velocity at t, has to be negative to say the direction is, now it's going down at that time. So that was like the random algebra. I don't think we've ever done the quadratic formula once in class so far. That happened in the middle of this one. And again, if this was an exam question, I'd rig the numbers so that it factors kind of easily, since those are the kind of problems that we've mostly encountered ourselves. But any other questions with this one? Yeah, you bet. Thanks for asking about it. So plug in those times and you'll get the velocities. Well, it looks like we're about out of time. Again, thanks for asking about that one. If you have other questions on any other problems on this set, don't hesitate to email. I'll be happy to help out. But have a great weekend, folks. I'll see you all on next class.